everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to start with module 5 in the course Engineering Physics, and we are going to discuss about simple harmonic oscillator. So before starting our topic today, let us have a brief outline of module 5. So in module 5, we are going to discuss about simple harmonic oscillators. In simple harmonic oscillators, we are going to discuss mechanical as well as electrical oscillators. So we may call them as SMHO, which represents simple mechanical harmonic oscillator, and also we will discuss SEHO, simple electrical harmonic oscillators. Then we have damped harmonic oscillators, where we'll be discussing about the damping. In simple harmonic oscillators, we are only going to discuss about the harmonic oscillations without considering the damping. But in damped harmonic oscillators, we are going to introduce the factor that is caused due to damping. And then we'll discuss the forced harmonic oscillator, where the oscillations will be forced oscillations. And then we'll discuss about waves. In waves, we are going to classify the waves into transverse and longitudinal waves, and also we are going to derive a wave equation, a general wave equation for a string, and then apply it to transverse as well as longitudinal waves. And also we are going to discuss about the reflection and transmission of waves at boundaries. So whenever the waves are traveling in one direction, how they transmit, and when they reflect, how the wave changes. That is what we are going to discuss here in reflection and transmission of waves. And then finally we are going to discuss about the harmonic waves. Now in today's topic for discussion is simple harmonic oscillators. So how we are going to discuss this topic? First we'll see the introduction. In introduction, we will start from what an oscillator is. What is an oscillation? And then we will see what is simple harmonic oscillation. And also we will define the terms that are involved in simple harmonic motion. So all the basics that are involved we are going to discuss today first, and then go into the subject. Then we will see the famous Hooke's law. And then we'll derive the expression for simple mechanical harmonic oscillator. And then we'll derive the expression for the energy of a simple mechanical harmonic oscillator. First, the equation for simple mechanical oscillator. And then we'll derive the expression for energy also for a simple mechanical harmonic oscillator. And then discuss about the conservation of energy. We know energy can neither be created nor destroyed. It can only be conserved. How this energy is changing from one form to the other form in a simple mechanical harmonic oscillator. And then we'll also discuss about the simple electrical harmonic oscillator. Now coming to oscillation. First, let us try to understand what an oscillation is. One complete to and fro motion of an object is known as oscillation. So here let us focus on to and fro motion. So to understand this, we will take the simple example of a simple pendulum. We will consider an example of simple pendulum to understand what oscillations are. So in a simple pendulum, what we have is a small bob which is attached to a light inextensible string, and one end of it is fixed to a rigid support. So this is the rigid support. And this is the string. And this is the bob. This is the bob. Now we say when we are just suspending this bob with the help of a string from a rigid support, we say this is the equilibrium point, or we also call it as the mean position. In other words, we say it is mean position, equilibrium point or the mean position. Now, when we disturb this bob, means I just take the bob here to here and leave it. I just disturb it from the equilibrium position, means I will take it to one end and leave it. Then what happens? The bob keeps on oscillating. So if I say this is the start position, actually this is the equilibrium position, but I'm taking it to one extreme end and I'm leaving it so that this becomes the starting point for this particular oscillation. So now what happens? This will keep on oscillating like this. So it will go in this direction first and again come back here. So I will call this as to and fro. This is one to and fro motion. So it is going in this direction and again coming back to the same point. So this is one complete oscillation. So the same thing applies when the object is taken to the other extreme. Suppose I bring it here and leave. So the object will start from here, it will move to the other end and again come back. This will become one oscillation. So this is to and this is fro. So one to and fro motion is called one oscillation, because whenever we are talking in simple harmonic motion, we'll be talking about one complete oscillation. So you need to understand what is an oscillation. So one complete to and fro motion of an object or a particle is called as oscillation. Now, if you consider from the mean position, if you are trying to calculate or count the oscillations from the mean position, so if the object starts from here, the mean position, so it will go to one end, come to this equilibrium position, go to the other end, again come back. So this becomes one complete oscillation when we take from the mean position. Okay, so I hope what an oscillation is clear. Now, the next thing we need to understand is these oscillations are periodic in nature. Periodic here means whatever repeats itself after regular intervals of time, we call it is a period. Suppose you see when you are attending the lectures, you will have the first period, second period, third period and so on. Why do we call them as periods? Because they are repeating at regular intervals of time. Suppose the Monday first lecture you have physics. So the next Monday first lecture again it will be physics. Of course you may have many lectures in between, but how they are repeating, if they are repeating after periodic intervals of time. And again also 1 hour duration, after each hour the next lecture repeats. So whatever repeats at regular intervals of time, we call it as period. So these oscillations are periodic in nature. So when I say periodic, if it is making 2 oscillations in the first second, in the next second also it will make 2 oscillations and the next second and so on. So we call them as periodic oscillations. If you see the example, the swing which we see in our day-to-day life. So you can see the swing here. Okay, so this is the best example of oscillations which are periodic in nature. So if you see, this is the equilibrium position, one to and fro motion. This is one to and fro motion. It makes one oscillation. And the simple pendulum we have already discussed. Now, simple harmonic motion is the simplest example of oscillatory motion. We have seen what an oscillatory motion is. One to and fro motion is called one oscillatory motion. Now, simple harmonic motion, which we also in short form we say SHM. SHM stands for simple harmonic motion. It is the simplest example of oscillatory motion. So when an object moves to and fro along a straight line, it performs simple harmonic motion. So if I say there is an object which is here, it is moving along a straight line, going here, again coming back, going in the other direction, and again coming back. So this is the equilibrium position. So this is along a straight line. So here also it is making one to and fro motion, and they are periodic. So you call it as simple harmonic motion. So the best example for the simple harmonic motion along a straight line is the needle of a sewing machine. Needle of a sewing machine. You all know the sewing machine. So if you take the needle, how the needle moves? It moves up and down about a fixed position or about the mean position. So we call it as simple harmonic motion. And all examples of oscillatory motion are examples of simple harmonic motion. So whichever is in oscillatory motion, they are the examples of simple harmonic motion. Maybe the term may be new for you, but you are very much familiar with the oscillatory motion. So all examples of oscillatory motion are examples of simple harmonic motion. Now let us come to the definitions. So we'll now define what is a simple harmonic motion. A motion in which acceleration is directly proportional to the displacement and is directed towards the mean position is called simple harmonic motion. So in simple words, I say acceleration directly proportional to displacement. A, the acceleration is directly proportional to displacement. So let us first understand this phenomena with the help of this diagram. So in this diagram, what we see here is a mass M, a block of mass M we have considered, and a spring is attached to this mass. One end of the spring is attached to the mass and the other end is put to a fixed support. So this is a fixed support. So what we are doing here, to the spring, one end is fixed and to the other end we are attaching a mass. Okay, a block of mass M. And this is the equilibrium position, means at rest. I say O is the equilibrium position. Now, the first step what we do is, we will pull this block to a distance, through a distance x. Means, we are displacing this mass through a distance x and leaving it here. Okay, so what is the displacement here? X. And when we leave it here, so we understand that it is a spring. When you are moving it here and leaving, the spring will start vibrating about the block will vibrate about the mean position. It will move back and forth. So now this mass will come with a force F. So the mass is coming with a force F. So what we try to understand here, that is why we have kept the word force. Even though we say acceleration is directly proportional to the displacement, we can also say that force is directly proportional to displacement, because we know F is equal to ma. Force is the product of mass and acceleration. And throughout this experiment, we are keeping the mass constant. So when m is constant, if A varies, F varies. If acceleration is directly proportional to the displacement, the force is also proportional to the displacement. So that is why we have put force is directly proportional to the displacement. So what do we understand by force directly proportional to displacement? More the displacement, more the force. That brings it back to the original position or the equilibrium position. So I'm displacing it through a greater distance. So the force that acts on it is also more. So this force we will call it as restoring force. This force is called as restoring force. So in a motion in which the force or the acceleration is directly proportional to the displacement and is directed towards the mean position. So the second step is directed towards the mean position. Means if this is the equilibrium position, when we displace it here, the body will vibrate about the mean position, oscillate about the mean position, but it will come back to the mean position. Means whichever direction it goes, the restoring force is always towards the mean position. I will take the next example. In this example, we have displaced it through a distance x towards the left. So when we have pushed it or compressed it, then what happens through a distance x? So definitely the mass will not stay back here. It is attached to the spring. So it will come back. So the force acts in the opposite direction. And it is called the restoring force, which tries to bring it back to the equilibrium position. So two things we need to understand. The acceleration is directly proportional to the displacement and it is always directed towards the mean position. So the first point is this and the second point is the direction. Direction here is always directed towards the mean position. Then you say it is in simple harmonic motion. So if you have to write the definition, you have to put everything in a nutshell. A motion in which acceleration is directly proportional to the displacement means more the displacement, more the acceleration, and this is always directed towards the mean position. Then we call it as simple harmonic motion. Now, what are the conditions for simple harmonic motion? For a system to contain simple harmonic motion, it should satisfy the following conditions. What are the conditions that the system has to satisfy to sustain simple harmonic motion? So the first one is restoring force. Means there should be a force which brings the object back to its original position. Only then you can continue with this simple harmonic motion. So restoring force is the force that tries to bring back the object to its equilibrium position. Then comes the inertia. What is inertia? It is the inability of a body to change its state of position by itself. Means if a body is in motion, it continues to be in motion. It cannot come to rest on its own. And if a body is at rest, it continues to be at rest. It cannot be put in motion without applying any force. So that is what we call it as inertia. So the system needs inertia. And then it should be frictionless. Now we have taken the example of a block moving on a surface which is attached to a spring. Now, if the friction between the block and the surface is more, then the block cannot move freely. So what we need is a frictionless surface. So these three are the main conditions for sustaining simple harmonic motion. Now let us see the other terms that are involved in simple harmonic motion. The first one is displacement, which is denoted by x. Generally, we denote displacement by x. So when a body is vibrating, its distance from the mean position changes with time. So whenever we are considering a body which is vibrating, okay, its distance from the mean position changes with time. Means at the initial point of time, if the object is at the mean position, as the time changes, the position also changes. So the value of its distance from the mean position at any time is known as the instantaneous displacement. So let us understand this displacement with the help of this diagram. Now what we have here, we are considering a mass, a block of mass m, which is attached to a spring. Okay. Suppose I pull the spring down, bring the block down and leave it. So what happens? This will keep on oscillating like this to and fro. So if I put it exactly, it is like this. It will go up, come to the equilibrium position, again come down and come back to the equilibrium position. So one to and fro motion is called one oscillation. So now suppose we imagine at time t is equal to 0 seconds, the object is here at the mean position. Okay, and it takes say 4 seconds to complete one oscillation. I'm giving you a simplest example. It takes 4 seconds to complete one oscillation. Now, at t is equal to 1 second, at t is equal to 1 second, the object may come from here to here. So, from here to here, it will take 1 second. Again, to come back from the extreme position to the mean position, it will take 1 second. Again, from mean to the other extreme, it will take 1 second. And to come back again, 1 second. This is how we are dividing the time interval. 4 seconds. For 1/4 of the oscillation, it is taking 1 second. So now, if you try to understand at a given point of time, how it changes with time. So at 0 seconds where the object is here. After 1 second where the object is here. At 2 seconds, the object is again at the mean position. At 3 seconds, the object is here. And 4 seconds, it is here. So now we can trace the position of the object at different intervals of time. So now what we are talking is the value of the distance from the mean position. So whenever we are measuring the displacement, it is always with respect to the mean position. So from here to here, we measure the displacement. So that is called the instantaneous displacement. Now when we are talking about the spring which is moving, we can also plot it in the form of a graph. How at t is equal to 0 seconds, the object is here. Suppose if it is starting from the extreme position. Suppose I am considering the oscillation like this. I have brought the spring here and I left it. So it will come here and again come back. So this is one complete oscillation. So at t is equal to 0 seconds, it is at the extreme position. And after t by 4 seconds, it comes to the mean position. And t by 2 seconds, it will be at the other extreme. 3t by 4, it is at the mean and t seconds. So here, the time period is t seconds. So in t seconds, we are able to trace where the object is at every t by 4 seconds. So in t seconds, it is completing one oscillation. So this is one complete oscillation. Starting from the extreme and again reaching to the extreme position. This is one complete oscillation and it is taking t seconds. So we are able to trace at different time where the object is. So that is what we will call it as the displacement. Now coming to amplitude, which we denoted by capital A. Amplitude is denoted always by capital A. The maximum value of displacement from the mean position is called as amplitude. The maximum value of displacement means if the object is starting from here, at 0 seconds it is here and at t by 4 seconds it is here. Okay, say at a time interval in between 0 and t seconds, or I can say at 0.2 seconds, the particle can be somewhere here. In between, it can be somewhere here. So when you see this interval of t seconds, so as the object moves, the maximum displacement, this is the maximum displacement it can have in the upward direction, and this is the maximum displacement in the downward direction. So the maximum value of displacement from its mean position is called as amplitude. And then what is the time period? the time taken to complete one oscillation is called as time period. Time taken to complete one oscillation is called as time period. And this time period T depends upon the mass and also the spring constant. M here represents the mass of the block. Here we are talking about a block of mass M. So it is the mass of the block or the mass considered in the system. And K here is the spring constant. So the time taken for one complete oscillation. So in this case, it is starting from extreme position and again it is coming to the extreme position. So the time taken, we are calling it as the time period T. So which is denoted by capital T. The instantaneous time or any interval of time we denote by small t. But time period is always denoted by capital T. Next is the frequency. So what is frequency? It is the number of oscillations made per second. The number of oscillations made per second, we call it as frequency, or the formula if you write F is equal to 1 by T. So this is very important relation. If you have to understand the relationship between the time period and frequency. So how frequency depends upon the time period. Okay. So to understand this, we will see this example. I have already given this example. T is equal to 4 seconds means the time it takes to complete one oscillation is 4 seconds. Now, if I am talking about a simple pendulum, it is taking 4 seconds to complete one oscillation. So if I say in 1 second, how many oscillations will it make? It will make only 1/4 of the oscillation because from here to here it will take 1 second. From here to here it will take 1 second. From here to here 1 second and again to come back 1 second. So in 1 second it is completing only 1/4 of the oscillation. So the frequency F is only 1/4 cycle. So that is how we try to understand. So we write F is equal to 1 upon T, that is 1 by 4. So hope this example is clear. Now let us take another example where the time period is 1 second. Means it is completing one oscillation in 1 second. Means the frequency is 1. Because what is frequency? The number of oscillations completed in 1 second. So for 1 second, it is making one complete oscillation. So F is equal to 1. Okay. Now we'll take it the other way. If F is equal to 4 means if it is making 4 oscillations in 1 second, then what will be the time taken for one oscillation? It will be only 1 by 4 second. So in 1/4 second, it will complete one oscillation. So therefore, in 1 second, it can make 4 oscillations. So that is how we need to understand the relationship between frequency and time period. Now coming to the phase angle, which is denoted by theta. Phase angle specifies the angular displacement as well as the direction of the point executing the simple harmonic motion. In other words, I'll say it tells about the state of vibration of the particle. So it also specifies the angular displacement and gives the state of vibration, the direction in which it is executing the simple harmonic motion. And it is given by theta is equal to omega t, where omega is the angular frequency and t is the time. Now let us understand angular frequency, which is denoted by omega. Omega here, the Greek alphabet we are using omega. This is small omega. It denotes the angular frequency. So the rate of change of phase with respect to time is known as angular frequency. Means omega can be written as theta upon t. Theta is what? Phase. T is time. Means the rate at which the phase changes, that is with respect to time we are talking about, is called as angular frequency. Now, when we write omega is equal to theta by t, so you can measure the angle at any given interval of time and you can find the angular frequency. Now, we'll try to understand. We will project a simple harmonic motion along the circumference of a circle and try to get the relation. So, what we are trying to understand here is, if you consider a particle which starts from here and it is moving along the circumference of a circle like this, this is one complete oscillation. Now, if the particle is moving like this, if I say, then the foot of the perpendicular that is drawn onto this diameter, okay, a perpendicular is drawn and this is the foot. So, as the particle moves like this, then what happens? The foot of the perpendicular moves along the diameter. It makes a simple harmonic motion. Means when the object is here, it is here. Now, when you take the object here, it is coming back here. So, the object is here, here. So, when the object is coming into this position, again it is coming back here. So, as the object moves along the circumference of a circle, the foot of the perpendicular makes simple harmonic motion along its diameter. So, now how do I put it here in this formula? So, when the object moves from here and makes one complete rotation, what is the angle through which it is moving? Theta will be equal to 360. So, in one complete rotation, it moves through an angle of 360, that is nothing but 2 pi. And the time taken for one complete rotation, we are calling it as time period t. So, for theta, we put 2 pi and for t, we put capital T. So, omega is equal to 2 pi upon capital T. And we also know that F is equal to 1 upon T. So, in place of 1 upon T, we can put F. So, we can also write it as 2 pi F. So, now omega, the general formula is theta by T. And for one complete oscillation, when we are considering, we are writing it as 2 pi upon capital T or 2 pi F. Now, the time period T is given by 2 pi under root m by k. Now, we will substitute it here in this formula and get the formula for omega. Since omega is equal to 2 pi by t, and what is our t? 2 pi under root m by k. So, 2 pi and 2 pi will get cancelled. So, this under root m by k, if it goes to the numerator, it will become under root k by m. So, omega is equal to under root k by m, or omega square is equal to k by m. So, we are going to use, in all expressions, we are going to use this formula omega square is equal to k by m, or the angular frequency omega is equal to under root k by m. Even in the derivation, when we are going to derive the expression for a simple harmonic oscillator, we will be using this. So, this comes from our basic definition for angular frequency. Now, what are the characteristics of simple harmonic motion? The restoring force is directly proportional to the displacement from the mean position, and the restoring force is always directed towards the mean position. So, these 2 points we have already discussed in simple harmonic motion. Now, when it comes to simple harmonic oscillator, I said we are talking about 2 types: mechanical simple harmonic oscillator and electrical simple harmonic oscillator. So, noted by SMHO or SEHO. So, first in mechanical oscillations, we will derive the equation of motion and then the expression for the energy and then conservation of energy. We will understand how energy is conserved in this motion. And the same thing for electrical oscillations also. We will see the equation of motion, then the expression for energy and also the conservation of energy. Now, we'll understand the simple mechanical harmonic oscillator. So till now we were talking only about simple harmonic motion. Now we are talking about simple mechanical harmonic oscillator. Maybe the name looks big, but the phenomenon remains the same. So whatever we have considered before, we are considering the same. A spring block system is the simplest example of a simple mechanical harmonic oscillator. So we are going to discuss simple mechanical harmonic oscillator. So in a simple mechanical harmonic oscillator, what we have? We have a spring block system. So this is the block of mass m and this is the spring. Okay. And one end of it is attached to the block and the other end is attached to a rigid support or a fixed support. So consider a block of mass m attached to a spring which in turn is fixed to a rigid wall. So we have seen one end is fixed to the block, one end of the spring and the other end is fixed to the rigid block. And the block rests on a frictionless surface. So when we have seen the conditions for simple harmonic motion, we have discussed that the surface should be frictionless. So the surface on which the block moves, this block will move now. When we disturb its position and leave because of the spring, it will move back and forth. And this surface should be frictionless. If this surface has friction, then this block cannot move freely. Now, the first point we understand, when we do not pull the spring, that is, there is no force applied on it. It is in equilibrium position. Now, we have just attached the block and left it. Means we are not applying any force. We are neither pulling it nor pushing it. Then what happens? The object is in equilibrium because there is no force that is acting on the object. The net force acting on it is 0. So whenever there is no force, the object is in equilibrium position. The object, if this is the equilibrium position, this is after moving through a distance x. So without applying any force, the object will always be in the equilibrium position. So let us now perform two actions. The first one is the pull. We pull the block outwards. So to my right, I will consider it as outwards. So it is the pull. So there is a force acting on the block that tries to pull it inwards. That is towards the equilibrium position. Now you imagine the block is here at the equilibrium position. I have pulled it through a distance x. Now there will be a force, action and reaction. Whenever there is action, there is always a reaction. So when I am pulling it towards the right, there is always a force that acts on the block that tries to bring it back to the normal position or the equilibrium position. So this is what we are calling it as a force that tries to pull it inwards towards the equilibrium position. And next, when we try to push the block inward, means from here, I will try to push it inward. Then what happens? There will be a force that acts in the opposite direction that tries to bring it outwards, again towards the equilibrium position. If this is pull, if this direction is pull, it will try to come back in the opposite direction towards the equilibrium. If I try to push it here to the left, it will always try to come towards the right, outwards towards the equilibrium position. So what we are trying to understand, two things, always it is directed towards the mean position or the equilibrium position. So in both the cases, we see there is a force acting on the block that tries to return the block to its equilibrium position. This is very important. And this force, we call it as a restoring force. So the restoring force tries to bring the object back to its equilibrium position. And the force law for simple harmonic motion is based on this force. So when we are deriving the expression or when we are calculating the force for a simple harmonic motion, it is based on this restoring force. Now let us see Hooke's law. Hooke is the name of the scientist who gave this law. So it is named after the scientist Hooke as Hooke's law. So in Hooke's law, what we are saying is, if the mass is displaced from the equilibrium, the spring will exert a restoring force. So in both the cases we have seen, if you are trying to pull it outward, it comes inward. If you are trying to push it inward, it will come outward. So in both the cases, the restoring force tries to restore it to the equilibrium position. So it is called the restoring force. And this restoring force is directly proportional to the displacement. So I write F is proportional to X. So F here is the restoring force. Now, if you consider K as the spring constant, I can remove the proportionality sign and put a constant K. If I am writing the proportionality sign, I'll write equal to. So there should be some constant. The constant here is K, which is the spring constant. This is K is the spring constant. And X here is the displacement. The displacement of the object is X. And now what does this negative sign denote? It denotes that the restoring force and the displacement are always opposite in direction. If I am trying to pull the object in this direction, the restoring force will be trying to bring it back to the equilibrium position. If I try to push the object in this direction, the restoring force will try to bring it back to the mean position. So in both the cases, you see the displacement is in this direction. That means the force will be in the opposite direction. The restoring force is always opposite to the direction of displacement. So we are having a negative sign. F is proportional to X, which shows that as the displacement increases, the restoring force also increases. And now we are writing F is equal to minus Kx. Minus denotes that it is opposite in direction. Now let us write the equation. We have already seen F is equal to minus Kx. Let us denote it by 1. Now if A is the acceleration that is produced by the force F in the mass spring system at any instant, according to the Newton's law of motion, second law of motion, F is equal to ma. So whenever there is a force that is acting on a body and the body is in motion and it is accelerating, so it should obey the law F is equal to ma. Here we have F is equal to minus Kx, and here according to the Newton's second law we have F is equal to ma. What is A here? Acceleration, and acceleration is given by rate of change of velocity, or it is also written as d square xy dt square, because velocity is rate of change of displacement. So I can write it otherwise, d by dt of what is velocity? Dx by dt. So that's why we are getting d square x by dt square. So we are writing F is equal to ma as F is equal to m into d square x by dt square. Let this be equation 2. Now if you see, the left hand side is the same. In equation 1, F is equal to minus Kx. In equation 2, F is equal to m into d square x by dt square. So if the left hand side is the same, the right hand side also has to be same. We will equate. Equating 1 and 2. We have m into d square x by dt square is equal to minus Kx. Or I'll bring this m onto the other side. We have d square x by dt square is equal to minus k by m into x. Or I can bring the minus onto the other side. We will have plus k by m into x. And we have already discussed this k by m, where k is the spring constant and omega is the angular frequency. So here we have seen omega is equal to under root k by m, or omega square is equal to k by m. So in place of k by m, what we are going to substitute is omega square. So what will be the equation? D square x by dt square plus omega square x is equal to 0. This is equation 4. So this represents the equation of motion for a simple mechanical harmonic oscillator. Okay, I hope you understand. Let me quickly write down the steps in the derivation. First, we started with F is equal to minus Kx from Hooke's law, because the displacement is proportional to the force. F is proportional to x and K we are taking as a spring constant. Then we have taken the Newton's second law, F is equal to ma, and we have written it in terms of x. The acceleration we are writing in terms of x. So this is m into d square x by dt square. So this is the second equation we got. Now we are going to equate 1 and 2. Equate 1 and 2. So if the left hand side is the same, the right hand side also can be equated. So I can write m into d square x by dt square is equal to minus kx, or d square x by dt square is equal to minus k by m into x. Or I can take it on to the other side. If this is equation 3, I can take this term on the other side, d square x by dt square minus k by m into x. If it comes onto this side, it will become plus k by m into x is equal to 0, because we want to write an equation. So this is of the second order, this is of the first order. So d square x by dt square plus k by m into x is equal to 0. Now we are going to make a substitution. Omega is equal to under root k by m. So omega square will be equal to k by m. I'll square on both sides here, we get k by m. So I can write this equation as d square x by dt square plus omega square x is equal to 0. So this is the expression for a simple mechanical harmonic oscillator. So equation for SMHO, simple mechanical harmonic oscillator. Now let us understand the motion, displacement in simple harmonic motion. So now we have seen the equation d square x by dt square plus omega square x is equal to 0. In this equation, if you try to get the solution, that is, find the value of x. So x is equal to a cos omega t plus phi. So the solution to this equation is given by x is equal to a cos omega t plus phi. So if you know the displacement, you can plot the graph or the curve. Now let us see. At t is equal to 0, what will be the displacement? So when I put t is equal to 0 here, omega t is 0 and cos 0 is equal to 1. So I can write x is equal to a. At t is equal to 0, x is equal to a. Means at time t is equal to 0, if I am plotting a graph with time along the x-axis and displacement along the y-axis. This x is the displacement along the y-axis and time along the x-axis. Now at different intervals of time, where is the particle or where is the object we are going to trace? So at time t is equal to 0, the displacement is a. It is maximum. I can say this is the maximum displacement it can have. So it is here at t is equal to 0. Now at time t is equal to t by 4 seconds. So what is the displacement? X is equal to a cos omega is 2 pi by t and t here is t by 4 seconds. We are taking plus 5. T and t will get cancelled. So this will be cos pi by 2. So cos 90 is what? 0. So 0 into a is 0. So x is equal to 0. So at t by 4 seconds, the particle is at 0. The displacement is 0. So if you see here, this will be at t by 4 seconds, the particle is at 0. Means the displacement is 0. So we have seen at t is equal to 0, it is at a. At t is equal to t by 4 seconds, the particle is at the mean position or at 0. Then at t by 2 seconds, the particle will be at the other extreme. If I put here t by 2, then what we will have is pi cos 90 plus 90 we can take. So that will be minus a. So the particle will be at the other extreme. So 0, t by 4, t by 2. So this will be 3t by 4 and this will be at t. So what we are trying to understand is in a period t, how the particle is, how the displacement of the particle is. If you see here, we are showing the time t is equal to 0. So at time t is equal to 0, the particle is here, that is at the extreme position, plus xm. Now, when we see at time t is equal to t by 4, the particle is at the mean position, this is at 0. Then at time t by 2 seconds, the particle is at the other extreme, minus xm. And at 3t by 4 seconds, it is at the mean position. At t seconds, again, it is at the extreme. So what we are trying to understand is a time interval of t is equal to 0 to t is equal to t. Means a complete oscillation. The time period is what? It is the time taken for one complete oscillation. So we are trying to trace the object on a graph which is plotted for time versus displacement, time along the x-axis and displacement along the y-axis. So here the displacement is at t is equal to 0, t by 4, t by 2, 3t by 4 and t. So if I trace the particle, this is one complete oscillation. This is one complete oscillation. It is starting from the extreme position, again coming back to the same position. So this is how we find the displacement. Now how do we get the velocity? So the velocity v is given by dx by dt. So we already have derived the expression for x. X is equal to a cos omega t plus phi. So what is velocity? Velocity is dx by dt. So I can put it as d by dt of x, that is a cos omega t plus phi. So taking the derivative, I take a is the amplitude which is a constant. I'll keep it outside. So d by dt of cos omega t will be minus sin omega t plus phi into, for omega t it will be omega. So we'll rearrange the terms and write, I'll put minus here, a omega sin omega t plus phi. So the velocity is given by minus a omega sin omega t plus phi. Then how do we get the acceleration? So means if you have an object which is moving, which is making simple harmonic motion, you can get the displacement from the equation. The solution gives us the displacement, and once you get the displacement, you can find the velocity as well as the acceleration also. So the acceleration is given by dv by dt. So dv by dt here is d by dt of v. So we write a is equal to dv by dt. I'll write it as d by dt of v. What is v here? A omega minus a omega sin omega t plus phi. I will put the constants outside, minus a omega. Now d by dt of sin omega t plus phi. Derivative of sin is cos. So cos omega t plus phi into omega. For omega t we get omega. So we can write minus a omega into omega will be minus omega square a cos omega t plus phi. So this will give us the acceleration. So the acceleration is given by minus a omega square cos omega t plus phi. So that is what we are going to see about the velocity and the acceleration. So if you want to see the waveforms, how the waveforms are going to be, all these expressions we have derived, x is equal to a cos omega t plus phi. So the velocity is given by minus omega a sin omega t plus phi. Acceleration is given by minus omega square a cos omega t plus phi. Now, if this phi here is the initial phase, if it is 0, then we have x is equal to simply a cos omega t. But if there is a phase difference of pi by 2, if there is a phase difference of pi by 2, so omega t plus pi by 2 or pi by 2 plus omega t, it will become sine. So sine and cos, sometimes we denote it in terms of sine function or cos function. Only difference you have to understand here is it differs in phase by pi by 2. So when we are talking about cos omega t plus phi, it is starting from the extreme position. When we talk in terms of sin omega t plus phi, it will start from the mean position. Now we have already traced this curve for the displacement. So if this is the displacement, this will be the velocity, because v is given by minus omega a sin omega t plus phi. So at t is equal to 0, sin 0 is 0. So the velocity will be 0. Means when the particle is at the extreme position, its velocity is 0. And when the particle is at the mean position, the velocity is maximum. So these 2 points are very important for us to understand harmonic oscillations. So again, if you see, if it comes to the extreme position, again it becomes 0. So how, with the help of the waveforms, we can understand or relate displacement with velocity. And now coming to the acceleration. So what happens when the particle is at the extreme position? The acceleration is maximum, but in the opposite direction, because we have seen that it is always directed towards the mean position. The restoring force always acts in the opposite direction and is directed towards the mean position. So here it is in the opposite direction. Here it is in the upward direction, displacement. Acceleration here is in the downward direction. So when this is minimum, this is also minimum. So at the mean position, the acceleration is minimum. So with this, I think we will stop our discussion and we'll continue it in the next class. For more details regarding this, you can refer to books by Cengage Publications, Engineering Physics, and also you can refer to Gaur and Gupta, Engineering Physics. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.